Alrighty, let's take a look at our homework for lesson 1.2.1. First, we're going to start off with the M&Ms. And these M&Ms are just kind of reminding you of the nature of proportional relationships. Remember, a couple basic ideas of proportions is the fact that the situation for 0, 0 absolutely applies to all proportional relationships, and it always forms a straight line. So that means that there's a constant growth rate, or what we would refer to as the unit rate. So in a situation like this, where you got 3 pounds of chicken costs $7, that particular piece right there is the data point for 3 pounds of chicken. But if you wanted to find the unit rate, that would be the price per pound. Then it'd be like, okay, so it's $7 for 3 pounds. How much would it be for 1 pound? And you may recall that we would do the division. 3 goes into 7 twice with a remainder of 1. So that means that your unit rate is going to be $2, and I guess we would round that down to 33 cents per pound. So that's the unit rate. That's how much it's growing by per pound. And of course, 0, 0 applies, because if you don't buy any pounds of chicken, you won't spend any money. So that's where the 0, 0 comes into play. And here, I guess your unit rate would be somewhere around there, but that's kind of hard to tell with the scaling that's going on. Now, this is a situation that is non-proportional because it doesn't pass through 0, 0. So the video game arcade costs $5 to enter, and then $1 per game. So if it was free entry and all you did was pay per game, then it would become proportional, because 1 game would be $1, 5 games would be $5, and so on and so forth. But according to this, you have to pay $5 even if you don't play any games. So it's not a 0, 0, it's a 0, 5. So here, instead of starting at the origin and being a straight line, it starts at y is equal to 5. That's like your y-intercept. And then it goes up by $1 per game that you play. Now, notice how this is not a continuous graph. This is a discrete graph, because you're not going to play 1.7 games. There's no fractional number of games in between. You're either going to play 1, 2, 3, 4, or 0, or whatever. They're going to be whole numbers. Whereas here, for the pounds of chicken, literally, it could be any number of pounds. You know, you could buy a package that was 5.62 pounds of chicken, and you just pay the appropriate price at $2.33 per pound. So this one is continuous with the line going through all those points, because you literally could have any number of pounds for the chicken. Okay, so let's read through these situations and see which ones are proportional and which ones are not. Kareem is ordering video games. Each game costs $39.99, and there is a shipping charge. Okay, so you have to pay that. So, I mean, one might say, well, if you don't buy any video games, you don't spend any money and you don't pay the shipping charge, right? That is correct. However, it's not really the 0, 0 for the proportional relationships, because the moment you buy one, you're not paying $39.99. You're paying this plus that. So essentially, the y-intercept becomes $4.85. And that gets added to however many games you plan on buying times $39.99. So if x is equal to 0, yeah, I guess I kind of see your point, but you are committing to buying it, so the 0 really doesn't apply in this situation. You'd either buy 1 or 2 or 3 or 4 or whatever. So it is definitely not a proportional situation because of that shipping fee. A given rectangle has an area of 20 square feet. What is the length? Well, this is non-proportional because it's not a straight line situation. So you could have one point at 0 or at 120, you could have another one at 210, and then another one at 4, 5. And if you plotted those points, they absolutely would not form a straight line. I believe the graph looks something like that. It's kind of, if this was your y-axis and this was your x-axis, your graph would end up looking something like this. And it's impossible for it to have 0, 0. Remember, the proportional relationships have to pass through 0, 0 and be a straight line. Um, you can't have the area of a rectangle have either the base or the height be 0. That would be impossible. And then Oleg ran 8.8 miles in one. Let me get rid of all that stuff. 8.8 miles in 1 hour and 20 minutes. Assuming it continues at a constant rate, that's the key to the straight line. How long would it take him to run a number of miles? Okay, well, we all agree that if he doesn't go anywhere, he's spending no time running, and vice versa. If he spends no time running, he will not go anywhere. Thus, 0, 0 applies to this situation. So constant rate of speed and 0, 0 applies makes this definitely a proportional situation. All right, let's take a little time on this. This homework is going to last longer than 10 minutes. I can feel it. All right, so Jerome is keeping track of how many books he and his friends have read during the first 100 days of school. To help Jerome present the data to his teacher, make a box plot of how many books each person has read. Okay, so for the box plot, you need this data right here. You need the minimum, the maximum, the median, and then the 2 quartiles. So everything is based on kind of ordering this data. So the first thing I'm going to do is I'm going to count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's nice because that means I'm going to have a number right in the middle for our median. So let's just put them in order. So you got 9. Looks like 12 comes next. Then we've got 2 17s and an 18. We've got, oh, there was a 14 in there. Well, let's go ahead and do this. Let's put the 14 there, then this other 17, and then the 18 can go here. So I've got the 14, and then we've got 20, 21, 24, 25, and 31. So let's make sure we got 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, now I'm going to highlight my minimum and my maximum. My minimum, there's my maximum, minimum, maximum. I'm going to highlight my median. Number in the middle is the 6th number, right? 1, 2, 3, 4, 5 to the left, 1, 2, 3, 4, 5 to the right. So there is our median. And then when we find the quartiles, we have to take everything below the median, and the number in the middle of that data is 14, and everything above the median, the middle of that data is 24. So there's your lower quartile is the 14, and your upper quartile, or your third quartile, is the 24. So we will take a properly scaled number line. The 9 goes right around here. The 14 would be right around here. The 18 is going to be somewhere around here. The 24 would be there, and the 31 would be there. So we would find where those points are on the number line and bring them straight down to create our minimum maximum. Our median goes in the middle, and then we box in the inner quartile range. Okay, so when we did this last year, we used some tools, online tools that were very helpful. We did this for the Ms. Pac-Man tournament. This is just kind of a review, just making sure basically that you understand the elements that are required for any box plot and how to find these parts. All right, rational number operations. I really don't want to go through and show the work for every single one of these. So my recommendation is check your answers, look through your work to see where you might have made a mistake if you got an answer wrong. And if you can't figure it out, then jump back onto our virtual meeting or bring it up today during our meeting so you can ask me to work that out, and I'll explain how to do these problems for you. Okay? Pause all you like until you get everything taken care of. I'm going to move on. So if you don't want to move on, pause until you're ready. All right, look at each graph below and write a story. Okay, so obviously there are going to be a lot of different stories that people are going to write. So if you look at mine, and if it's similar in idea to how yours is, then great. If you want to ask me if your story sounds like it makes sense during our virtual meeting time, then yes, I'll listen to your story as well. Here for A, you've got the speed appears to be increasing as time goes on. So this is kind of an example of what acceleration would look like, right? Because as time goes on, you're getting faster. It's not a distance that you're going. You're actually going, the speed is increasing over time. Here, it is a similar idea where you've got a rapid increase in speed, and then once you get up to a certain speed, then you start cruising at that speed. You're not getting faster or slower. So this kind of reminds me of like when you have an on-ramp getting onto the highway, how you're at the stop sign or at the stoplight, and then you've got the opportunity to get onto the on-ramp, and then you're speeding up because you want to get up to the same speed as all the other cars already driving on the freeway, so you don't get run over by a semi or something. So but once you get there, you don't want to speed, you don't want to keep accelerating like we did there, so it levels off. And then here, this is one where you're starting off. I picture this like a rocket. You know when they launch a rocket, how at first it's hardly moving, and then it just starts to lift off the launch pad, and then as it goes up higher, it's gaining in speed. So yeah, the speed in this case is accelerating over time. Where this was a constant rate of acceleration, this one was started off slower and then got really, really fast, like a rocket would. All right, Riley was monitoring the growth of his favorite tomato plant and collected the data as shown at the right. So I imagine the time in days. Usually we use that for our x-axis, our independent variable, because we want to see how much has it grown over X amount of days. So the height is your y. Oop, look what I forgot to do. Very bad. I did not label my axes. There we go. Fixed it. Okay. So yeah, notice how for the most part it looks like it's kind of a straight line, but after day 20, it starts to grow even faster. So what did I say here? The plant grows faster as the days go by. Yeah. So here it looks like it's growing at kind of a constant rate, but then it starts to go up. Similar to this one, it was going up at a constant rate of acceleration, but it started off like this, and then toward the later days, it starts to grow even faster. All right, I think that's it for our homework. How much time did that take us? Not too bad. We're done in less than 13 minutes. So, all right, so good job. Hopefully, you're starting to understand a lot of these concepts that we're learning in this chapter. Remember, most of this chapter is primarily review. It's when we get into chapters 2, 3, and 4, when we start taking stuff we learned in previous years and building on them, or learning some brand new stuff. So good job. Make sure that you're completing your homework, and look, please follow that direction right there. Anytime it asks you to graph, the more graphing you do, the easier it becomes, and the better prepared you're going to be for high school. So take advantage of this in your homework. You can make mistakes on your graphs and fix them. But when you get into high school, it's going to be expected that you know how to graph. So make sure you're practicing this now. All right, take care. Bye. Bye.
Hey, feeling good, like I should. When in dark, walk